I have a small company where we work with machine learning, and it's this is not working. So this is it. I hope you like the presentation. Yeah? Okay, so I have to stand here, okay. Actually, this is interesting. We have a lot of clients who require machine learning from us, and this slide, they're really big companies, and this slide is not here to impress you. This is because this impresses me. Why would these huge companies, like one of the largest media companies in the world and so on, why would they go and just talk to some random guy in Eastern Europe? It's a bit strange. And the fact is that there's a big mismatch between supply and demand, as you probably know. I guess all of you do machine learning, the people here, so there's a lot of demand and not much supply, so there's a lot of opportunity there. And the reason for this is that in the academic world, this is an interesting intersection between the academia and practical, pragmatic engineering. Okay, the people in academia, they produce a lot of software, and it's that funny software where you have single-letter variable names and you know how it works, and you just don't touch it so it doesn't break. And then there's the programmers, and they're very good at programming, but sometimes the math part can be scary. So the intersection is really in high demand. And I want to demonstrate this on an example of Word2vec, which was an algorithm that was published by Google more than a year ago. How many of you have heard of Word2vec, or almost everybody? Okay, so I can skip the introduction maybe. I just want to show you one thing in the, just so everybody's on the same page, I'll just show you what it does quickly, okay? So basically it's a method. Can you click on the link at the bottom? Or maybe I'll be giving you instructions so I don't have to walk there, okay? So just click here. Yeah. Cool, so it's an algorithm, and it's an unsupervised algorithm which learns representations for words. What that means is for each word, let's say dog, we have a vector of numbers, and that's not so interesting. The interesting thing is that it learns the vectors in such a way that the vectors realize relationships between different words. So car is to cars as dog is to dogs. Okay, that's the similarities in this space, which can be exploited to do some analogy. So for example, if we, on the input, we have the word man, which really is the vector for the word man, and we have the word for king, we subtract that from that vector, we add another vector to it, so very simple operations. We just operate on the vectors, okay? We just add, subtract, and so on, and we ask, the result again is a vector, these are all vectors, so we get a vector as the output of these two operations. And we ask, what is the closest vector to that? Okay, just similarity, cosine similarity. And if you click here on this little question mark here, you should see queen, which is also what we would expect looking at these things. Man is to king as woman is to queen. That makes sense for us. So that's the exciting part. That's why people were excited when Word2vec came out, because it's pretty simple, and still it does interesting things. And it also has some practical applicability, which maybe I'll talk about later, but we can also find similar words. So for iPhone, this is iPhone, you can't see it very well, but if you click again, get most similar, you get iPad. That's what the model was learned. But automatically, there were no people annotating the texts. It just, on input, it got a huge corpus of 100 billion words, and just by looking at these words and doing something with it, without annotations, it learns these things. Can you click on the USA here? USA, can you click on that? No, just click on it. This is advanced UI. And then get most similar. So there you go. You can't fool the machine, so that's what Word2vec thinks. And so on. You can do various things, and that's all I wanted to say about Word2vec. Oh, can you go back to the presentation, please? There we go. So that's what it does. Now, I have a lot of slides on theory, but most of you know theory, so I'll just skip through the beginning. maybe just a summary. What it basically does is it goes through these unannotated words, and for each word in a sentence, it tries to predict the other words around it. That's the core of it. It's this image here, it's the skip gram architecture. You have a word, and you try to predict the words before it and the words after it. And you try to do it in a specific way, which is summarized here. This is the softmax equation. This is not going to be about equations, but just so you have an idea, each word is associated with two different vectors, okay? Two different vectors. You just you multiply them to get some number, then you normalize here, and that's all there is. This is pretty slow, so there were some optimizations in Word2vec where they do hierarchical things. So instead of evaluating this on the entire vocabulary, this summation here that goes over the entire vocabulary is very slow. So instead, they just evaluate on some specific words as they arrange them into a binary and so on. Not that interesting. The practical side of it, they also released Tomáš Mikolov, our colleague from Brno. Maybe some of you know him. He also released a C tool that actually realized the training. So this was not just an academic paper, just some equations and you do the rest. It was a real paper, and he also released some real models. So that was, I think, a big part of why this was successful, why not only in academia, but it also had a lot of media attention. And so probably part of it is because it was, released by Google. So it's just brand association. It's an effect which I call if Google farts, the rest of the world shits. It's like anything they produce is great by definition. And here, how many of you know Python? Almost everybody, okay. So for those of you who don't know, it's just a language which is very good for prototyping, for quickly creating prototypes, and it's also good for teaching. But it has a very bad reputation in that it's slow. So I try to optimize this, basically the Word2vec algorithm to run in Python, and with pretty good results. This is not what I want to talk about today. Okay, I already gave this talk several times, and it's actually on YouTube. So if you're interested in that part, you can watch it at YouTube. Or maybe a few words. So in pure Python, everything is very slow. That's true. Okay, there's no question about it. Then there's a library called NumPy, which realizes some basic matrix operations and operations with vectors, and it's faster. And as you can see, it's about 20 times. The first line is the NumPy speed. Okay. The second line was the C tool, the one released by Google, and it was nicely optimized, so that was a good benchmark. And the NumPy is like 20 times slower. Okay, so that wasn't good. Nobody would be using that. So then I went and optimized some specific hotspots and so on. And I also used extra libraries which you can link to from Python and which are super optimized for the particular processor you're using. This is maybe too technical, but if you do that, you can actually get a higher speed. It's faster than the C code, which sounds unbelievable. How can a Python program be faster than C? But that's because you plug into these low-level Fortran or whatever it is libraries, and you get like 3 times faster execution in the end. So that was interesting. So the end result, I also did some parallelization, which means it can run on multiple cores. If you have a multi-core machine, as most of them are these days, you get an extra speed up and so on, so it's very fast. You can watch the details on YouTube, but what I wanted to talk about today was what happened after that, because this was already 1 year ago, okay, long time in this area. And what people tried, I especially like this article, which was about trying to see what actually the similarity is, because, okay, iPhone is similar to iPad, but what does it mean? Maybe we want a different application, and the similarity we want to mean something else. So can we tweak it? What is it that Word2vec actually finds? And these gentlemen from Israel, they did some very nice experiments on that. Basically, what they did, earlier I told you each word is associated with each word tries to predict the words around it. That's the idea, right? And here they changed it that each word was trying to predict not the words around it, but context around it. And the context can be words. It can also be something else. So it's like a generalization. Okay, this context can be different things. And I'll give you an example here. As the context, they chose some syntactic properties of the words around it. Okay, so it's not words, it's this, something is a preposition after, before, and so on. So they decouple the words from the context. So maybe we have like 50,000 distinct words in the vocabulary, and we have completely different number of contexts. So these two are now decoupled. And they tried training, it's the same algorithm, but now it has a different meaning, and they asked a question, what does that do? And they came up with, I think, a very interesting results, because this is exactly what I like. Here there is an example, again, this is from the paper. I don't know if you can read it or if we can zoom, but if the input word is Turing, Alan Turing, the scientist, now these two columns are the most similar words to Turing, according to Word2vec. So it's non-deterministic, finite state, computability, what you would expect, so that's pretty good. But if we try this dependency context instead of words, that's the last column here, we get words which serve the same role. They call it a functional similarity. So we get Pauling, Hoteling, Hamming, and so on, scientists. Okay? So somebody who serves the same role as Turing. Or here with Florida, Word2vec gives you the cities in Florida, things that are related to Florida in that domain. Okay? And the functional similarities give you basically other states in the United States. So different type of similarity. So that was a very interesting piece of research. I hope they follow up with this, with different types of contexts and so on, because I think this is more practical than playing with optimizations and so on. I think this is more, let's skip through that. A bit later, the people from Stanford, they released a very nice paper on what they call GLVs, global vectors. And they started from a different point. They started, instead of just putting some formula, they started thinking, okay, if we want similar words to be similar, what should the similarity function look like? Okay, they start like from first principles. So it should be symmetric, and then they reason, it's very nicely written, they reason about that there should be an intermediate word which somehow relates to both, or they should have this property and so on. And in the end, they come up with an objective function, and surprised that is exactly what Word2vec does. So they just join the result of Word2vec, but from a different direction. And this was super interesting, because by doing that, they also understand how to compute it differently, because now we understand better what Word2vec does. So what you can do is you build a matrix, a two-dimensional table, where the columns are the words, the rows are the words, the columns are the contexts. It can be a square matrix if you have words and words, but we already said the context can be generalized to whatever, so let's say a rectangular matrix. And now each cell in that matrix is how many times did these two occur together. Just an integer number, 0 times, 5 times, 100 times. And when you take a logarithm of that, then that is you get again some matrix, okay? Just take a log. And now when you factorize this matrix, you get exactly the Word2vec vectors. You factorize it into two separate matrices. Okay, when you multiply these two factors, you get the original one. That's factorization. Hopefully, you know factorization. I'm not going to go into that. So, but this is a fundamentally different way. So instead of Word2vec just goes through the sentences and tries to predict and sees where it made error, and by backpropagation it tries to adjust the model. This one just counts this huge matrix of word by context numbers. Okay, doesn't do any training, no neural networks. It just counts the integers, takes a log, and then factorizes that. And it's faster, obviously, as a result. So that was another nice property. They explained Word2vec, and they also found another way of computing it, or a particular version of it. But there was a problem with the paper. The theory part was very nice, but the practical part was, this is being recorded, so it was not so nice. In the experimental section, they just pulled numbers from different papers without actually replicating the results. So they were comparing apples to oranges. Okay, the numbers didn't mean anything. And then based on that, they claimed that the method is like 11 or whatever it was, 15% better than Word2vec, which is a huge number. So a lot of people got excited, but the experimental section was just flawed. The numbers were not really real. And the people who called them out on it were these, again, the people from the Israel University of Paralelni. And then the Richard Socher and the Stanford people, they went back and said, okay, that wasn't good. We already addressed it, now it's better, but it still performs better. And Goldberg went back and said, well, okay, we didn't mean to say, like, your version was bad or something, or that you suck, but it still sucks. Basically, that's what they replied. So there was some back and forth. And as a result, in case you're wondering, the accuracy when you control for all the parameters that are there, because it's not Word2vec, a single algorithm, but it has many little things you can tweak, how big the window is from which you extract the contexts, and where you do some subsampling, and how you compute the vectors and so on. So when you control for that and do the same thing for both algorithms, basically, you get the same results. So that's the conclusion of these experiments. So that was probably what you would expect, actually. So, yeah. So don't get fooled by bad experiments. That was the message there. And then again, the same people, they did. They did some more work into what Word2vec does. I already said it was solved by GloVe, but actually Word2vec, that's like a whole family of different algorithms. It just has a common name. You can do the hierarchical, softmax. You can do negative sampling, which is something else. Instead of normalizing everything, you just take some sample. Maybe I'll talk about this in more detail. So, okay, so for each, we take the word and we try to predict the context. That's the basic idea again. But then what negative sampling does, it takes the word and tries to predict random context, something that is not there, like negative examples, from classification. You have some positive, some negative. So the positive one, what's in the actual window of context, and then it takes maybe 10. For each positive one, it just randomly takes 10 negative ones. That's Word2vec with negative sampling. And they analyzed this negative sampling variation of Word2vec. And again, they were able, it's again a very nice paper, and they were able to derive an analytical solution. So like with GloVe, again, you just count how many times things occur together. I highlighted that's this part. How many times did a word and a context occur together? Just an integer, 5, 100, whatever. And how many times did the word occur on its own, like a marginal count? How many times did the context appear alone? This is everything summed, like a normalization. Again, you take a log and you're done. Yeah, so again, the negative sampling has a simple analytical solution, let's say, the objective function. And this maybe some of you realize is this formula. It's very, in natural language processing, it's one of the most famous ones. That's point-wise mutual information, PMI. It's used all around for detecting collocations and so on. It's a very standard formula. So that was nice that, again, it connected to a body of knowledge that we already had. And so that was, I like these papers that connect things that were, in one way it's always nice that we build deep networks and it's just basically throwing more parameters at it, okay? I trained a network with 5 layers. I trained 20 layers on better, But that's, in a way, that's not really satisfying, because science, it's about, finding connections between things that were previously unconnected, which is essentially reducing the number of parameters, not expanding. Okay, so negative sampling, they found the connection to PMI, and there was an extra twist here. Not only can we take this PMI matrix and again factorize it, like they did in GloVe, they said, okay, so how about we take this matrix directly, no factorization. Just take the rows and that's the word vector. Yeah, we don't factorize it anymore. Just take the row. Basically this is one cell in that matrix, so take that row, that will be our vector, and we can compute the similarities and the analogies and so on directly on that. Yeah, could be visualized better, but hopefully you have the picture of what I mean. And the difference here is that this matrix is super sparse, of course. Like most words and most contexts, they never appear together. Yeah, most of the things in that matrix are 0. So it's a very large matrix, number of words times number of contexts, but it's very sparse. So, and they had their own experimental section where they evaluate these different combinations. This SGNS, that's the skipgram, that's Word2vec basically, yeah, with the negative sampling, SGNS. Then they have their own PMI, that's what I just described. I think they have GLAF2, maybe that's on the next slide. This SVD, that's when you take the PMI matrix and you can factorize it again. So here they use SVD, which is, most of you know the most famous factorization algorithm. So they just factorize it and take the left factors from SVD and use that as the word embeddings. So they try that as well and evaluate lots of different experiments. The K here that you see, that's the number of negative samples that you use. For each positive one, we generate some random negative ones. So do we generate just one negative or 50 negatives? So they try to explore this parameter space. Maybe let me go back here. Here. If you see, this discussion basically was in November, so 1 month, let's say 2 months ago. So we're almost up to the present. And now I'll take you to the future. So this paper hasn't been published yet, so it's being reviewed. And they tried even more experiments because it's really a mess. Most of you heard of Word2vec, but really to apply it properly, you have to know what these little parameters that I talked about, how to tweak them. Like it gives a lot of difference in the result, which is not very nice. That's not very practical. You know, it's not like you plug your corpus in and you get something out and you're happy. Or you can be happy, but you can do better probably. So what they do is they run many different experiments with many. There we go. Many different, like how big is the window? Do we use subsampling? In the SVD factorization, what do we do with the spectrum, with the singular values? Do we just throw it away, or do we multiply the left singular vectors with it? Do we scale them? This is the subsampling. How many negative samples to draw? And there were also, this is also interesting, in the Word2vec, there's things that you can find in the paper. If you read the paper, you have some idea of how it works. But actually a lot of, well, not a lot of, but some parameters are hidden in the implementation. So if you just implement what's in the paper, you'll get a different algorithm basically. Because, for example, what they do is, what Tomáš Mikolov did in his implementation is, when you have a context window and it contains words that you're not interested in, you can ignore them, throw them away. But that effectively makes the window larger. If you had 10 words and you throw away some of them, then it shrinks, and the words that were maybe 5 words apart are now just 1 word apart. Okay, so the window is like effectively larger. It sounds like a little thing, but this window has a big impact on how especially the semantic task performs. So it can again make a lot of difference. So they tried these different parameters and explored the methods. The PMIs is what I said, the large sparse matrix. This is the same matrix factorized by SVD. This is Word2vec with negative sampling, and GLAF is the one by the people from Stanford. So they try different parameters. They have more tables in that paper with some results. And even better, they have a section at the end which summarizes these results in words. So it gives you some hints of what to do if you want to achieve something. So when is subsampling good? What values of what to do with the spectrum in SVD, and so on. So I think this is a practical paper. They basically just run different, combinations of parameters and see what happens. But I think this is what was lacking in that space. So very nice paper. We're almost at the end. I'm not sure how long this was supposed to take, but maybe just a few words about the point of this. So how would I say it? So the practicality makes a big part of a successful algorithm. And I mean it in the way that changing one line of code, let me give you another example. So in the implementation, there's something that's not mentioned in the paper. And that is that if you do this operation, the man minus king plus woman, and you're looking for the most similar vector, which should be queen, okay? But if the most similar word is actually man, one of your input words, you ignore it. You go down the list to the second ranking most similar. If it's woman, you ignore it again, and so on until you hit the first one that's not one of the 3 input words. Hopefully it's queen. But this is not mentioned anywhere, so some people actually try to implement it exactly how it's described, taking the first ranking vector, even if it's man again, or king. And they got, of course, worse results. Yeah. So this is like a little thing that's not mentioned anywhere, but it has a practical, like a lot of you, I guess, are PhD students, okay? So if you develop your own algorithm, you want to compare it to Word2vec, and you implement it as it is in the paper, and you get rubbish results, you can't publish it, they kick you out of PhD, or I don't know, your girlfriend leaves you, you jump off Charles Bridge, I don't know. So this can have like big implications for what you do, and there's a movement for open research, which I'm sure you know about. So this was, I mentioned a little bit about trauma of, how people did experiments, poorly, and that was corrected. But at the same time, this is very good because the implementation was released in the first place. So you could actually see what's happening, and you could port it like I did to a different language, or compare it against your own version and so on. So this is a positive thing, like that's what happens in science. You just try this and that and something sticks. But this is maybe the point of this presentation, to make something useful, you release the implementation as well. It's just don't rely on the papers and the formulas which are in the papers. Okay, thanks, that's it. And now I don't know how this works, but I have more than half an hour, so we can chat, or you can ask me questions or whatever.
So I'd like to ask a question. First, thanks for the presentation.
You're welcome.
It's nice to finally have a presentation in English here. I'd like to ask what are the kinds of tasks that this was measured with? I mean, the tables have multiple columns, and it seems there are multiple tasks, so which are some of the popular tasks?
Yeah, they're all pretty artificial. That's one of the problems with these techniques, that nobody really knows what to use them for. Like, the original idea was you can plug these, the word embeddings, the vectors for each word. Yeah? So you can plug them into classification or into some other tasks, and it will improve these other tasks. Now, can you do it in a different way without these unsupervised embeddings? Well, yes, you can, I guess. That's one question. This column are the Word2vec analogies, the man to king and so on. But they also tried on some other, you see there's like 7 of these different data sets. So they tried in their experiment, they tried to cover not just the analogies, but just also some word similarities, and I don't know, some of these are, but.
So the Google analogies,
that's this one.
How big is the data, or what kind of relations?
It's about 15,000 questions. So the question is man is to king as woman is to, and then you have to fill in that. So there's like 15,000 of such questions.
Right.
Yeah.
So it's trained on a general problem. So
it's a what?
Are all these algorithms trained on a general
Yeah, on the same one. Yeah, that was the point of these experiments that they.
So my question is, how big of a boost can we expect if you train it on some specific algorithms, for example, law literature or something like that?
You mean with this type of evaluation, or your own evaluation for your company? This one. With a larger corpus. Okay, I can.
With a specific corpus, domain-specific corpus, like for example, technical reviews or something like that.
Then I guess the questions which deal with technical stuff will work better. But yeah, well, I mean that's a very good question. How, if we have a specific thing we want to do, And this is again going back to what I said about the dependency context. We want to do something specific, or maybe iPhone. We don't want iPad to be the most similar. We want iPhone 5 or I don't know, something else. So what do we do as a company? How do we do that? So we change the corpus, or maybe tweak some parameters or something? Or these are very good questions. Yeah.
Did you try it on different languages, Czech?
Yeah, some. Good question. Some people I know tried with German and with Dutch, using the implement. But Czech. I don't know of people trying this in Czech. Sorry.
The question is, there is something in the structure of it, or in the structure of the language in which we're training it, which can also influence.
For sure, yeah.
Setting, which parameter setting is the right one or the best one.
Yeah, English is super simple, primitive morphology, so of course that helps. You can do the plurals easily. You couldn't do that in.
I think on the first meetup, we were shown Word2vec on Czech.
Yeah, well,
There you go. You can tell me.
I trained it, but I didn't know if they actually did any sort of evaluation on how
Yeah.
it works.
Yeah. I would assume that maybe doing more pre-processing would help there, like lemmatization. Get some. These models were not really, especially the one that Google released. There was no pre-processing, not even lowercasing. Okay, they just used whatever was there. But for these highly, inflected languages, that's.
Maybe I can comment. I'm not sure if Google used Word2vec for that, but they had very interesting work on translations, where they basically take English sentence, they know translations of some words to Spanish, and they fill in the translation of the remaining words which they don't know to Spanish based on the word that it means. So it's quite good.
Another application. Also, what we used Word2vec for was in entity linking. Basically, you have a lot of surface forms that you need to build your training set. You want to fix the typing errors and so on, to unify them and say that's the same entity. So we used Word2vec to give us some hints of which surface forms could be the same one actually. Like, I don't know, Barack Obama, who knows how to spell that, correctly. So there are many versions. So, yeah.
Can you say a bit more how do you use this model in real life?
How do we use it? We didn't use it much. No, we didn't use it much. No, just what I said and that's it. I mean, when Google released it, it caused big waves because it's Google and it looked interesting, but really the most interesting applications I saw were these little toys of Man is to King and whatever, these silly games. So, but I'm sure people are using it for interesting stuff. It just didn't, You use Word2vec when you want to demonstrate strategic innovation, okay? Because everybody knows it and it's there to impress the executives. But how does it really help when you want to improve like something really specific rather than word analogies? You have to test it. You mean this one? Okay, so you mean something else, sorry. So I think you mean this one. Yeah. But these are basically we have 15,000 questions we are asking, and some portion of them are called syntactic and some are called semantic. So you just take a subset and evaluate. Yeah.
So maybe back to the previous reaction and actually using the model, there's a big hype around Word2vec right now. We see it linked to some basic counting techniques and matrix factorization stuff has been used before in latency and semantic analysis and stuff like that. And you can see it convert in one table that's actually a pretty similar performance
Yeah, no, that's what I meant. I hope this doesn't sound like, what I said, it didn't sound like that I'm, trying to diss Word2vec. I think it's interesting, but, there's this phase when you just do new stuff and you don't really know what it means. Yeah, and then this phase, this contraction phase where people just try to figure out how it relates to what we did before. And that's what happened here. I think it's standard thing. So, and new things are coming after this, like people are always working, it's publish or perish, so there's always stuff coming out.
So do you foresee that there's something really new coming with the neural network-based models of creating distributed representations of words as compared to the previous ones based on matrix factorization?
Yeah. With unsupervised methods, the evaluation is always tricky. It's practically impossible because if you can evaluate an unsupervised task, it basically becomes supervised task if you know what you want to do, yeah? So it's like by definition you can't do that. But it's still good for building insight. When you have data and you don't know what's in it, then unsupervised techniques are good for that, like clustering and so on. So improving that task, I think it's valuable.
Right, true, but if you do the same with latency and technologies and stuff like that, I mean, if there's something really new coming with specifically Word2vec, and neural distributed representations of neural network-based language models. As you have practically.
Well, it is like fundamentally it is different because, like you say, the latent semantic analysis, that's a linear method, but neural networks can be nonlinear, so that's a different class of things they can solve.
Okay, so as compared to the basic algebra techniques, like you just don't count out the matrix, but you feed it through the logarithmic function and then factorize it. This sounds pretty simple.
Not very deep, huh? Deep learning. Yeah. I don't know. I think I'll pass on that answer.
Maybe if I can comment on the movement usage, what I noticed, I don't know, actually I wanted to ask the same question because I'm not aware of any direct usage of WordNet, but people are...
Are you saying WordNet or Word2vec?
Oh, sorry, Word2vec, because
Okay.
Then people are working on building on this distributed representation, and basically I think most of you have heard about the famous case of linking Word2vec to convolutional neural networks and image recognition. So basically they are annotating pictures by words, basically by connecting these distributed representations. And another direction which I think is pretty interesting is learning some relation functions in this vector space. For example, I think it was paper by Richard Sofer actually, where they were learning, basically they were given a lot of instances of some relation, like instance of, like California is instance of US state, Albert Einstein is instance of scientist and so on. And basically from these training samples, it was able to learn a generic mapping function in the vector space, which was able to perform the same relation on unseen instances. And also people are trying to build distributed representations of whole sentences. There was actually a paper where they were building distributed representations of whole sentences pretty much, and using that for translation. So they basically did mapping from sentences to this space, like for English and for example Spanish, and they just used it in reverse for Spanish after converting it into sentence, and basically the sentence in Spanish came out, and it's in development, but it was able to distinguish many nuances and stuff like that.
Thanks. Yes, the English-speaking person in this room.
I'm not familiar with Word2vec, but I would like to know how the word is represented as a vector, because it seems much clearer on the globe, but
Well, it's okay. So you have the mapping between words and their IDs, basically. So dog would be like 125 ID. And then you have this matrix where the rows are these IDs. So the row number 125 is just a sequence of numbers. You call that a vector, sequence of numbers, and that's it. So you go from dog to 125, and you take the row in the matrix.
But how? Because to be able to make a relationship within this words, the vector representation should have some structure, but I don't see how it passes from the.
Yeah, well, that's a good question. Yeah? How does it happen? That's the glove paper. I think from what I presented today, the glove paper is the best on explaining that, like giving some motivation why that should work. It's not obvious. You're completely right. Yeah. This one. That's it.
So, is there a source of good implementations of these algorithms and the various corpuses?
Yeah.
For basically benchmarking and stuff?
These guys, the Kohlberg and Levy, these are probably the best in that area, the ones who ran all these experiments and so on. But still, I was trying to replicate the results just to see if you want to understand something, you have to do it yourself. That's not just in machine learning, that applies to everything in life. So I tried to do it myself, this thing, and replicate the results, do the PMI stuff, take the log and do the SVD, and I couldn't replicate what they did. So I looked into it, of course, like why is that? Did I misunderstand the paper? And I asked them for the implementation as well, and it turns out they had a bug in it. Okay, so there was a bug, so I would probably recommend their work and the thing they did, but you have to be careful that it's just code that.
But did you use just the paper, or did they share also some data?
When I asked them, they also sent me the data, the code. About the data, these are like standard data sets. Where was it? These. So I guess you can download these from somewhere. This comes with Word2vec, and the others some evaluation challenges that are part of a conference or something. Bless you. Okay, thanks. Jensen, okay.
So I suppose it's already used somewhere in the instruction.
Yeah.
Some can you kind of describe the most interesting cases that actually solve some?
Sure, it's used. So for those of you that don't know, Gensim is like a software library that is targeting topic modeling. So unsupervised analysis of text. So people use it in companies to do topic modeling. Yeah. Okay, nice. So I don't know how this works, but I'll be around for another more minutes, so we can chat. I'm also interested in what you people do. This is just weird standing here and talking to an audience, but I would like to talk to you as well. Cheers.
First of all, thanks for the presentation.
My pleasure.
So how it works here, because I can see that there's many new faces here. So you are free to stay as long as you wish. Feel free